So hi, I'm Kurt, and I'll be talking about some kind of numerical analysis tips and tricks for DeFi audits with a focus on the TWAMM audit that Spearbit recently conducted. So for analyzing DeFi math, a few of the tools we'll talk about are just order of magnitude reasoning when you're doing over and underflow checking. Talk about testing the worst case first. Safety in the presence of rounding error, and I'll show you some SMT solver hacks. And like I mentioned, this is all in the context of the audit of the TWAMM mechanism, which is a time-weighted average price AMM. So it's basically Uniswap v2, but it also supports this long-term order primitive where you can say, I want to sell N tokens per block for 1,000 blocks or whatever. I don't know why I used a concrete number for one and a symbolic number for the other, but that's that's the way I did it. Hopefully that's clear. So it's just making long-term orders in case you aren't, you want to DCA, or you have a very large order that exceeds the liquidity of the pool, or you have no special market information and want to try to have less slippage. All right. So Spearbit audited the Cron Finance implementation, and a recurring theme throughout this audit was that there was a really strong desire for gas efficiency, but that led to a lot of optimizations that needed careful numerical analysis because, say, safe math was omitted, or we were using storage slot packing or something like that. And so I'll basically go through just a few different things. This talk isn't really about like, here are these awesome crits we found. Like, none of these things were critical vulnerabilities, although I think one was high severity. But one of the analyses I'm going to show you is like, actually, proving something that has minimal impact. And the idea is more around the process and the sorts of reasoning tools you can use rather than, trying to show off some cool findings or anything, although some of them are kind of cool. So that said, first thing I want to talk about is called the double overflow of scaled proceeds. And so to introduce this, when you make a long-term order, the proceeds, which means the tokens you purchase, those get accumulated in sort of a standard accumulator style variable. If you've worked with any sort of like yield protocol, like Yearn or anything else that kind of accumulates basically the earnings and then has to distribute them proportionally to them. You've seen some variant of this algorithm where you're just kind of tracking like total earnings, over, all, in this case, it's total purchases over all long-term orders. And then it gets scaled in the denominator, divided out by the, total amount of tokens being sold, and then to, recover some individual's purchase amount. Basically, you take the scaled proceeds at the whenever they're claiming, and then minus at the start, and you get this difference, and you multiply by what was their personal contribution to the sales rate throughout that, and get the number of tokens they've purchased. So that's a gas efficiency thing. And then for a further efficiency thing in the TWAMM, because you have two of these scaled proceeds values, one for each of the two tokens in the pool, packing them into a single storage slot saves a ton of gas, right? Because you're basically doing half as many S-store operations. This is the main, the core loop is going to be updating this variable frequently. So you pack them into 128-bit integers, but now you have kind of a very low overhead before these things can potentially overflow. And to overflow once in this addition here is fine, because only differences between values matter. But if it overflows twice, then you can lose money because basically the difference won't be correct anymore. So just to highlight a couple other things, so you see here this term on the right is the important one, because that's the increment for each order block interval. So for gas efficiency reasons, you don't calculate orders every single block. You let them build up for some number of blocks. Then in the denominator, you have that sales rate I mentioned, and then there's this scaling factor to protect against round-off error, which is 2 to the 64. And so this is the formula we want to analyze. So we're going to start by just estimating orders of magnitude of every term, basically, and what determines the order of magnitude, right? So the constant is the easiest one. That's 2 to the 64. That's about 10 to the 19th. We don't care about anything other than basically how big it is for this initial analysis. The sales rate, right? That's going to be the number of tokens you're selling per block, which we can bound that later, times 10 to whatever the decimals of that token being sold are. And then similarly for the tokens that are purchased, well, you're going to depend on what's the price of that token relative to the one that's being sold. You have this factor of the order block interval, because remember, it's per block in the denominator, but it's per order block interval in the numerator. So over several, that's just some number of blocks. Then you get a factor of n there, because basically the number of tokens is price time purchased is price times number of tokens sold, and of course a factor for the decimals. And so 2 to the 128th is about 10 to the 38th, and so that means this ratio needs to be small compared to 10 to the 19th for safety, right? Because we already have a factor of 10 to the 19th from this round off protection scaling factor. And so we look at that ratio. Okay, so the ratio, it depends on price, order block interval, and then the ratio of basically the unit value for each token. Which an interesting thing to note here is that actually the number of tokens you're selling per block actually cancels out. This factor is like price can vary a little bit, but price generally doesn't vary by like an order of magnitude, more than an order of magnitude or something like that. So that was an interesting thing already that popped up in the analysis, is that it actually doesn't matter how many tokens you're selling. It's just dependent basically on the price and the decimals, or the relative decimals. And so when you're looking at something like this, you always want to check the worst case first, like come up with the most extreme but reasonable example. And if things are fine for that, you can stop worrying about it, right? Because what you really want to do is prove that this isn't a problem and go find things that are actually bugs. And so we go back here briefly. So all right, what can be bad? Price imbalances or decimal imbalances. So I immediately kind of zoomed in on decimal imbalances because there can be rather large ones. The one I took was DAI is 18 decimals, GUSD is 2 decimals, and it's plausible that these might both be in a pool together because they're both stable coins. The price, of course, is easy to analyze. That's going to be about 1. The order block interval is just some number you have to look up from the code. In this case, it's not making a big contribution anyway. It's 64. But so then you calculate what's this ratio, and it's about 10 to the 17th, which is kind of close to 10 to the 19th, right? So we were hoping to prove that like this was totally fine, but it's probably not totally fine, so we need to analyze it a little more closely. And so we can calculate exactly how many order block intervals we need to overflow, and that turns out to be about 29. So well, how long is that? Well, 29 intervals of 64 blocks, 12 seconds per block, is about 6 hours, which is actually a really short time. And this is well below what the intended safe length of time for an order was supposed to be, which was 5 years. So that's an issue. Now the next step at this point was actually just to write a test and make sure all the math and reasoning was correct, because it's easy to miss something just in abstract reasoning. So always write a test to confirm. But we're gonna not bore you with the details of the code here in the talk. So other things to note about this issue, price differences are also dangerous. All right, so like if you have a DAI WBTC bool, which is 18 versus 8 decimals, but WBTC is a factor of 10 to the 4th times more valuable than DAI, and that would have an overflow time of just under 2 weeks. Which is also pretty bad, and it's worse than you would think just based on the decimals alone, because the price contributes. And an interesting thing is that imbalances can partially cancel out. For example, in a USDC ETH pool, USDC has very few decimals, but then ETH is much more valuable than USDC, so those actually go in opposite directions, and so it's like they had the same price and USDC was 10 decimals instead of 6, basically, because ETH is like 4 orders of magnitude more valuable. Right? And so a case like this actually caused the dev team to overlook the severity of the issue prior to the audit, because this was a thing where the dev team came and they said, yeah, we think this is fine, but we want you to look at it. And they had looked at some of these cases, but they had sort of picked ones where the decimals and the prices went in different directions. And so that underscores again the importance of make sure you're checking like a worst case. Because that'll tell you quickly if there theoretically could be a problem and whether you need to actually investigate more. Let's see. So I mentioned this previously, but so long as the price is at least bounded, your time to overflow doesn't depend on token sales rate. It's just an interesting math thing that shakes out. And the solution was, instead of hard coding 2 to the 64 as the scaling factor, you use a scaling factor based on the decimals of the token in the denominator, which means extreme prices could be an issue, but for reasonable tokens that currently exist, it's not a big deal. So actually, maybe let me just go back and say, so right here we have that hard coded 2 to the 64th. You replace that with 10 to the decimals of the token in the denominator, because that's really all you need to make it, avoid excessive rounding error. So you didn't actually need to scale by 10 to the 19th in all cases. All right, so that was the first issue. So that was highlighting how to do kind of order of magnitude analysis, and to check your worst case first. Let's talk about something that was an issue but was actually proven to not lead to any vulnerability. And this is this underflow in this little subtraction here. There's a comment here that hopefully explains why it can't underflow, but it actually can, because so this is in the logic for canceling a long-term order, and it turns out you can actually cancel an order after it's been completely filled, which does lead to this underflow here. And what this calculation is trying to do is figure out how many tokens basically you had said you were going to sell but didn't get sold because you've canceled your order early, so those will be sent back to you. And you see here there's this underflow, and if this value on the right hand side here works out to basically a number of tokens that is less than the total reserves of the pool, and also less than the total tokens queued to be sold, you could actually extract value here if you could get this refund U112 value in a reasonable range. And so then the challenge becomes, can you get it there? And so we can do our basic order of magnitude analysis. So this difference of the expiry block, so that's the block the order expires in, minus whatever the last virtual order block was, which means basically the last block that was processed by the AMM. That's always going to be basically 2 to the 256, right? Because I think roughly a billion blocks is hundreds of years, right? So and a billion is tiny compared to the 256, right? So that's always going to be about 10 to the 77, which that's a number I recommend just memorizing if you do a lot of this kind of analysis. To the 256 is about 10 to the 77. What's the sales rate going to be? Well, let's say you're selling 1,000,000,018 decimal tokens per block. I mean, that's probably an upper bound. So that's maybe up to 10 to the 27th or less than that. But now we've got this case where we've got a really big number that's close to the max UINT 256 multiplied by a number that's a lot smaller than the first number, but is still pretty big. So this multiplication is going to overflow a lot of times, and what you really care about is what's the remainder of that multiplication, mod 2 to the 256, to know whether the resulting value is something that's in a feasible range for what you could extract out of the contract. So you've got to get a little fancier with the math, and so what you want to try to do is rewrite this expression in a way where you can evaluate that mod easily. So to make the formulas a little smaller, I defined this value, which is basically the reverse of the subtraction. So it's the last virtual order block minus the expiry block. And, again, doing worst case analysis, that should be no more than about 10 to the 9th, which is several hundred years, so a definite overestimate. So we can be very confident it's, this number is no bigger than 10 to the 9th, let's say. And so then you can rewrite things. You notice I've made the modulus explicit now, so now the multiplications are proper mathematical multiplications. And you rearrange the terms a little bit, and you get this one value that is very, very small compared to 2 to the 256. So that's basically the 1 plus the block number difference times the sales rate, based on the upper bounds we assign to those, that's no more than maybe 10 to the 36. Maybe you say, well, maybe we could add a couple orders of magnitude to that even to be safe, but still that's going to be way less than 2 to the 256. And then you notice that first term, well, that's a nice multiple of 2 to the 256. And now we can evaluate the mod, so we can drop all the things that are multiplied by 2 to the 256 except for one leading factor of 2 to the 256. Because remember, we said the second term was very, very small compared to 2 to the 256. So we can safely, get something where we don't have a modulus involved anymore, and we can just look at its order of magnitude directly. And, so you have something that's like 10 to the 77 minus something that's a lot less than that, right? It's 10 to the 36 sounds big, but it's a tiny, tiny fraction of 10 to the 77. So this is still basically 10 to the 77, which is way more tokens than, are ever going to be in the contract. So it turns out that this is not actually, exploitable, although it's interesting to mention that it's sort of like one step away from being potentially exploitable, because if you could, say, manipulate something like that sales rate number to have a much larger value, you might be able to make that multiplication wrap around enough times to get to, a small refund, and you could actually get value out. So, it's because we didn't find any way to manipulate these other values in the expression, it was basically like, low risk. But it could be, combined with other things, that weren't there but hypothetically could be to become severe. So it's always good to fix these, even if they evaluate as, nothing bad is actually going to happen. But, that's how you decide, is it actually a risk or not, as, kind of figuring out, can you get in the dangerous range. All right. And then, so the last thing I want to talk about is, refactoring for gas and safety at the same time. Sometimes I want to show you how you can gas optimize and actually make the code safer. It is possible, believe it or not. So this came up in the core invariant calculation for the TWAMM, where you had these two checked subtractions. And the potential concern here is that if an underflow in those does occur, the TWAMM basically freezes up and can't process further trades, deposits, or withdrawals, right? So we always say, you want to be safe, you want to use safe math, but like safe math isn't necessarily very safe, right? Because something, reverting and not being able to process, that could make funds get stuck. That wouldn't be good. So we want to look at these subtractions and, see, is there any risk from them? So starting with the second one, this one is actually completely safe, and we could remove the safe math because the calculation is basically of this form where you have a number minus a number that's, less than or equal to it, because, right, the first term, you have that sum1 variable, and then you're subtracting off this AMM end token 1 thing, which if you look up, you see that that's basically, sum1 times the token 0 reserve, but then divided down by the token 0 reserve plus some other number, right? So AMM in token 1 is, at most sum1. So sum1 minus at most sum1 is at least 0, right? So that's correct by construction. You could remove that subtraction and, be in good shape. But what about this first line. The same reasoning actually doesn't apply here because there's a division that goes in the wrong way. So when you compute AMM n token 1, you have a div down here, and then you go and you divide something by AMM n token 1 in the next line. So you have a number that's a little bit smaller, potentially due to truncation, and then you divide by that number that's a little bit smaller than it should be. So when you divide by something a little smaller than it should be, it means you can get a result that's a little bigger than it should be. And you say, well, but there, the div down in the next line, maybe partially offsets that. And yeah, maybe it does in some cases, but you can't conclude that without further analysis. And so it turned out the best thing to do in this case, since we can't conclude whether this is safe as written, was actually just to rewrite it in a way that is safe. And I'll spare you the algebra, but the refactoring here on this slide is mathematically equivalent up to rounding error to the expression, the original expression. But you notice now we've constructed, both of the final values in such a way that they're explicitly of that form where it's a number minus a number that is, no bigger than the first number. And we've dropped the safe math now because we can, and so it's actually cheaper gas-wise. You can't get stuck due to an underflow. And another really nice benefit of this, by the way, this is just a general principle you can keep in mind, is that there's manifest symmetry if you interchange the 0 and 1 indices, which that's an invariant that the original constant product formula has. Right? It's, xy equals k is invariant under, changing, substitution of variables between x and y. So, anything you have that's, calculating update to that invariant should have that same symmetry, and if it doesn't, you've got a problem. And the first formula technically did have that symmetry, it was just hidden, but now the symmetry is there and it's obvious. So like that's, it obviously isn't sufficient to prove something correct, but it's, it's a good sanity check and a good thing you can use to try to spot bugs. And so anyway, during the audit, I actually moved on at this point because it's like, well, there's no reason really to try to care whether that initial formula was actually capable of freezing up, because we have something that's cheaper gas-wise and we can prove doesn't freeze up. But for the purpose of this talk, I thought it would be interesting to go back and see could it freeze up. And I mean, you could do this by hand with pencil and paper, but it's a lot more fun to use a thing called an SMT checker or an SMT solver, because that's a general tool you can apply elsewhere. So I thought would be fun to cover this. So what is SMT, first of all? So it refers to like a class of mathematical problem called satisfiability modulo theories. What's satisfiability? Well, that's the problem of whether some Boolean predicate has a satisfying assignment, which means values for the variables that make it evaluate to true. I mean, just to give an example, a Boolean predicate is like A and B, and a satisfying assignment would be, A equals true, B equals true, right? Because then true and true is true. So then theories in this context means mathematical objects like integers, rationals, reals, bit vectors. And so that means your Boolean predicates can include statements about these, objects from these theories. So like A less than B, where A and B are integers or rationals or something. And then an SMT solver will just try to find satisfying assignments to SMT expressions. So an example might be find an assignment for x is greater than 3 times y, and x minus y equals 1, and x is greater than 0, where x and y are integers. And it's pretty easy to come up with a satisfying assignment, x equals 1, y equals 0, right? Because 1 is greater than 3 times 0, 1 minus 0 is 1, and then 1 is greater than 0, right? And so yeah, people make programs called SMT solvers that do this assignment finding automatically. And so what we can do is we can transform our Solidity formula into a thing in an SMT solver. So I thought about doing a live demo, but live demos never work. So I just screenshotted the steps you'd use. So there's a solver called Z3. There are many others, but I use Z3 for this. It has a nice convenient Python API, which makes it nice. So there on the left, we're in Python, import the library, declare some integers, declare a solver. When this add function is basically adding conditions or constraints, right? So this is, adding to the conjunction of all conditions for our SMT problem. I've drawn some arrows here to show where things correspond. So like you can see that first double-sided arrow there is showing the correspondence between the final token 0 reserve calculation on the left and right, and you see it looks just like it does in the Solidity code. Basically, you just write your mathematical expression, but then to add a condition for verifying, because we want to try to find an underflow, right? Because that's a theory, is that maybe underflow is possible here. So we add this condition that sum 0 is less than the token 0 reserves at the end, and then we can call check on the model, and it returns this 3-letter sat that means satisfiable or satisfied. So it's telling us, oh yes, I did find an underflow, and then you can even cooler get what is the concrete solution out of that by doing s.model, and it gives you the set of initial input variables that you declared for the token reserves and the token inputs that actually results in an underflow, and then you can check it and make sure it's correct. This isn't a terribly interesting concrete solution because the numbers are like so tiny, right? So if you want to, you can add more constraints to get more realistic assignments. So I did that here. You can see in the box, I added some constraints to like make the token reserves be orders of magnitude that we would maybe expect in a DeFi world. And I also tried to constrain the token 0 input to try to get something that would be a realistic like exploit or something that maybe a hacker can achieve. I think this would actually be very hard to achieve in practice, because if you, at least in playing around with it, I found that basically one sales rate has to be extremely high, and the other one has to be extremely low. And by extremely high, I mean you have to be selling like more tokens per block than there are reserves of that token in the pool. So maybe this could happen in pools with like very, very low liquidity, and maybe also pools where like only one type of token is being sold, because otherwise like the value might be too high for the other, whatever one is supposed to be low. So it seems like this would be very hard to achieve in practice, but it was theoretically possible that you could freeze up these pools, it turns out. But because we were able to refactor it, we just didn't have to worry about that. And maybe as a last thing I'll add, you can also go ahead and check the refactoring with Z3. You don't really need to, because the reasoning was very simple. But hey, it's fun, and we see that when we put it in and do the check, it comes back unsat, which means unsatisfiable. So it's confirming like, yes, indeed, as you suspected, we can't get an underflow here. You can see how I formed the condition a little differently. I used an or, because if either one of them underflows, that's bad, right? In the sort of third line up there. All right. Anyway, that was all I had today. So hopefully you got something useful out of that. I realized it was a lot of like trying to talk about math, and I didn't have as much time to polish these up as I wanted to, but hopefully we can make up for it with any questions if something wasn't clear. I don't think so. I mean, you need to have a basic understanding of math, but I think like if we kind of go back, if you're able to understand the math that the code is doing, you can just type it in into the SMT checker, and it'll spit numbers out. You probably need to be pretty good at math to write an SMT solver, but any math that you're able to understand just from looking at it, you can put in there, and it's mostly just knowing what the API is. I'll just plug a little bit. At Maker, we've actually done a little bit of work on trying to make formal verification more accessible, and so there are some tutorials we've created, basic stuff that introduce things like Z3. So I'll share those in whatever Spearbit channel is most appropriate after the talk. Maybe that's Cantina or something. And people can check those out if they're interested. So I actually used one of those tutorials to remind myself how the Z3 Python API worked to do this talk. It depends a lot on what you're auditing. I have a tendency, for whatever reason, to end up auditing things that are math heavy for some reason. Maybe that's just, it's partially by personal preference, I think. But if you're doing anything in DeFi, I think you're not going to be able to avoid doing a certain amount of mathematical reasoning just because DeFi itself is so math heavy. And so many bugs are actually math bugs, especially as people implement, more complicated algorithms and stuff, right? Back when it was, really just like x, y equals k, and that was the most complicated thing. I mean, there was still plenty of like tricky math in that, but it's I'd say the complexity is only increasing. So. Yeah, specific to DeFi. I mean, there are a lot of good tools out there. Like I haven't used or tried all tools. Basic static analysis things like Slither are always good. I think being able to use an SMT solver it can be helpful in some cases. Being good with like a testing framework, is essential. Like I like Foundry, and Foundry has a lot of, good like fuzzing and stuff built into it as well. For fuzzing, you can also use something like Echidna, but yeah, you should be able to use like a unit test framework, a fuzzer, a static analysis tool, and then maybe like some sort of formal verification thing like an SMT checker, or there is maybe out of scope here, but there are various open source formal verification tools you can use, like Mithril, Manticore, HEVM, Halmos I saw was mentioned in the chat. That's a recent one. But yeah, that basic set of tools, and you can sort of pick and choose what you want, right? Like you can fuzz with Foundry or Echidna, either one. Like they have some relative pros and cons, but they're both good. And like if you want to write your tests in hard hat instead of Foundry, you could do that. But yeah. Anyway, I think that answered the question. Just have a unit test tool, a static analyzer, a fuzzer, and maybe some FV tools. Yeah, I can talk a little bit about what the experience was like. Yeah, this was definitely one of the most, I'd say, active audits I've been on in terms of findings and discussion, and going back and forth with the team on stuff. I feel like we had a really great team for this one because everybody meshed really well together, because there was like way too much for just one person to look at or investigate. So people did a really good job on this of just kind of splitting up and saying, well, hey, I'll go look at this, I'll go look at that. We had a lot of great discussions with the Cron Finance team while it was going on. Like they were very active in following what the issues were, giving us guidance on what they were worried about specifically in the code. Like that's something I always encourage when you're doing an audit, is like get the dev team's opinion on what are likely the problem areas, because they kind of know where they've done more checking versus less, or where they're a little less certain about something being safe or not. So that can be helpful. Yeah, and it was definitely I'd say a chaotic process in some ways, but it just kind of had to be, because there was so much information flying around, and keeping everything organized with GitHub issues. Like that maybe would be a thing I'd do differently going back, as we sort of waited to write a lot of things up till towards the end. And so maybe that's one learning is, yeah, maybe writing something up into a condensed issue a little sooner, would help basically transfer some of that stuff out of like, your mental RAM, into storage, so to speak. So maybe that would be a thing I would change. But yeah, overall it was a great audit experience and learned a lot during it. Well, I think some things are, going to be evergreen, and if you're an auditor, you'll just always need to know about stuff like reentrancy and other common classes of bugs. But I think there is a lot of room to specialize in different areas, as the complexity increases. So one obvious area might be like these kinds of numerical analysis and simulation. Another might be like financial or economic reasoning, because there's often a game theoretic level to these protocols beyond just like, did they implement their algorithm, correctly, but like, is their design actually economically sound? And, I'm sure there will be others as protocols become ever more specialized, right? Like, like you might have people who specialize in trading protocols or lending markets, or like derivative things like options and stuff, right? Because some of these demand a good bit of domain knowledge, right? Like, right now we've got an audit running for, yeah, there's an implementation of like an on-chain options thing, and you need to like kind of know something about Black-Scholes to really like evaluate, is that implemented correctly? And so, as more complicated stuff gets invented, it definitely creates opportunities for specialization. But I think auditors are always going to need to know the basic stuff as well. So, all right, yeah, thanks everybody for attending.